All right, strap in, everyone. Today we're going deep, really deep into some cutting-edge AI research.
Deeper than usual.
Oh, yeah, way deeper. We're talking about this paper that's been causing a stir, the Cosmos World Foundation Model Platform.
Cosmos WFM.
Yeah, Cosmos WFM. Like I said, this is not just another AI that can, tell a cat from a dog or something. This is different.
Totally different. This is about AI that learns, it basically learns how the world works, like the actual physics of it, just by watching videos.
It's like they're teaching a computer to see the world, but not just as pixels and images, but as a whole dynamic system, right, with rules and everything.
Exactly. The researchers who created this, they call them World Foundation Models, or WFMs for short. It's kind of like they're trying to capture the essence of how reality works, how our sonical world operates.
So it's almost like they're giving the AI,
A model of the world.
Yeah, a model of the world, like blueprint or something.
More like a simulation, really. Like, imagine an AI that can look at a stack of blocks and know exactly how they'll fall over before it even happens.
Okay, now that's just cool. But how do you even begin to teach an AI something as complex as physics?
Yeah.
Like, where do you even start?
That's the really fascinating part. See, they built these Cosmos WFMs in 2 stages, pre-training and then post-training.
Kind of like an apprenticeship.
Yeah, you could say that.
Okay, so pre-training, that's like the foundation then, right?
Exactly. That's where the AI gets the basics. And for this, they trained it on a massive, and I mean massive data set of video clips, 100 million of them.
100 million video clips. That's got to be like a zillion hours of footage.
Try 20 million hours. To put that in perspective, that's like watching videos nonstop for like over 2,000 years.
Wow. Talk about binge watching. But seriously, why so much video? Why did they need to show the AI so much stuff?
Because the idea is to expose the AI to as many different physical phenomena as possible. Like everything from gravity and how objects move to, cause and effect, all the basic rules of the world.
So it's kind of like showing a kid a bunch of videos of objects falling, bouncing, colliding, all to teach them how stuff works, right?
Right. But the key here is the sheer volume and diversity of the videos. The AI learns by seeing these concepts play out in millions of different ways.
But isn't there a risk of the AI getting kind of lost in all that data? Like, how do they make sure it's actually learning the right things?
That's where the careful curation of this data set comes in. It wasn't just a random collection of videos. They specifically chose clips that had lots of action, lots of visual information, the kind of stuff that would really teach the AI something.
So they had to be picky about their videos. They couldn't just use any old thing.
Exactly. And they even used another AI, a visual language model, to actually caption each clip.
Wait, so they used AI to train AI. That's wild. But why the captions? Why bother with that?
Think of it as giving the AI a little extra help, The captions provide context. It's like having a teacher there to explain what's happening in each scene.
Okay, that makes sense. So the captions are like a cheat sheet for the AI.
In a way, yeah. They help the AI understand what it's seeing.
So pre-training lays the groundwork, gives the AI the basic knowledge. What about post-training then? Is that where it gets specialized?
Exactly. Post-training is all about fine-tuning. They take these pre-trained WFMs and then they train them on smaller, more specific data sets, depending on what they want the AI to do.
So it's kind of like the AI goes to grad school and gets a PhD in a specific area.
You could say that. They tested it out with some really cool stuff like camera control, robotics, even autonomous driving.
Okay, now those sound interesting. Let's start with camera control. What does that even mean in the context of AI?
So imagine you're exploring a 3D world generated by AI, right?
Yeah.
And you can control the camera, just like in a video game.
I can see where this is going.
They trained a WFM to do just that. They fed it videos with specific camera movements, and the AI learned to predict how the scene would change as the camera moved.
So it's like the AI becomes a virtual cinematographer. It knows how to frame a shot.
Precisely.
That's wild.
Yeah.
What about the robotics part? How do these WFMs fit into that world?
Well, they did something similar, but with robots. They trained a WFM on real-world robot actions, so it could actually predict what would happen before the robot even moved.
So it's like they gave the robot a sixth sense or something, like it can see into the future.
In a way, yeah. It can anticipate the consequences of its actions.
That's incredible. So it's like the AI is helping the robot plan its moves more efficiently, right?
Yeah.
And adapt to unexpected situations.
Exactly. This could be huge for all sorts of things like manufacturing, logistics, even surgery.
Wow. And they used it for autonomous driving too, right?
Yep. That's another area where being able to predict what's going to happen is crucial.
Absolutely. Self-driving cars, they're the future, but there's still a lot of kinks to work out, especially when it comes to safety.
Right, you can't test a self-driving car in every single real-world situation, especially the dangerous ones. That's where simulations come in.
That's where these WFMs come in.
Exactly. With WFMs, you can create these incredibly detailed and realistic driving simulations, even for those rare edge case scenarios that you wouldn't normally be able to test.
It was like a virtual driving school for self-driving cars.
Exactly.
That's amazing. But how do they know that these WFMs are really understanding the laws of physics? Like, it's one thing to generate realistic-looking visuals, but how do they measure the AI's actual understanding?
That's a great question. And to test that, they came up with this thing called a physics alignment test.
A physics test for AI. I'm all ears.
Basically, they gave the WFM a bunch of real-world scenarios, like objects falling or colliding, and then they just watched to see how accurately the AI could predict what would happen next.
So it wasn't just about generating pretty pictures. The AI actually had to, show that it understood how physics works.
Exactly. It's the difference between an AI that can mimic reality and one that can actually, comprehend it.
I bet they had some pretty complex ways of evaluating those predictions, huh?
Oh, yeah, definitely. They used a whole bunch of different metrics. Like, they looked at things like pixel level accuracy, so comparing the predicted frames to the actual frames.
So, how closely did the AI's prediction match what actually happened down to the individual pixels?
Exactly. They also looked at feature level similarity, which basically measures how well the AI captures the important visual details, and then object level consistency, which is all about tracking the movement and interactions of objects.
Okay, that makes sense. So it wasn't just about getting the overall picture right. The AI also had to get the details right. How did the WFMs do? Did they pass their physics exams?
Well, they showed some really promising results. Not perfect, of course, but surprisingly accurate in a lot of cases.
So these WFMs are starting to look like pretty impressive students. But I gotta ask, what's going on under the hood? What kind of tech magic is making all this possible?
So at the heart of it all is this thing called the Cosmos tokenizer. It's kind of like a translator, it converts all that visual information from the videos into a language that the AI can understand.
So it's like turning a movie into a script that the AI can read.
Exactly. But instead of words, it uses these things called tokens. They're basically like compressed representations of the visual data.
So it's like they're taking all that complex visual information and boiling it down to these little bite-sized chunks that the AI can easily digest.
Right. And the cool thing is they actually developed a whole bunch of different tokenizers.
Different tokenizers for different types of data.
Yeah, like some are designed for images, some for videos, some can even handle different resolutions and aspect ratios. It's kind of like having a universal translator for the visual world.
That's super cool. So the AI is getting this really rich understanding of the visuals. But how do they actually train these models to understand and simulate physics?
Well, they experimented with two main techniques, diffusion models and autoregressive models. Each one has its own sort of strengths and weaknesses.
Okay, let's start with diffusion models. How do those work?
So imagine you take a perfectly clear image, right? And you start adding noise to it, little by little, until it's just completely scrambled.
You're intentionally messing up the image. Why would you do that?
Because then you train the AI to reverse that process, to learn how to remove all that noise and get back to the original image.
Okay, so it's like you're teaching the AI to be a master art restorer or something,
Right.
bringing a damaged painting back to life.
Exactly. And in that process of denoising, the AI learns to recognize the underlying structure and patterns in the data, even when they're hidden by all that noise.
So it's not just memorizing what the image looks like. It's actually learning about the relationships between the different parts of the image.
Right. And those relationships, they reflect the laws of physics, right? Like how objects are supposed to move and interact.
I see. So by learning to denoise, the AI is actually learning about the physics of the world.
Precisely. And then once the model is trained, you can just give it random noise and have it generate brand new images or videos that are both realistic and creative.
That's wild. And they use this diffusion model approach to train their WFMs.
Yeah, but with a bit of a twist. They used a specific type called latent diffusion models, which operate on those tokens we were talking about earlier, remember?
Ah, right, those compressed representations of the visual data. So it's like they're training the model on a more efficient version of the data, not the raw pixels themselves.
Exactly. It makes the whole training process a lot faster and more efficient.
Smart. And I bet they also used those captions we were talking about earlier to help guide the training process, didn't they?
Oh, absolutely. They integrated something called text conditioning. So they're basically feeding those captions into the diffusion model along with the visual data.
So they're teaching the AI to connect words and visuals, like to understand how language describes the physical world.
Exactly. It's like learning from textbooks and hands-on experience at the same time. And that combination of visual and textual information leads to a much deeper, richer understanding.
Makes sense. So that's diffusion models. What about those autoregressive models? How are they different?
Well, autoregressive models, they're all about prediction. It's like imagine you're trying to predict the next word in a sentence.
I'm pretty good at that.
Right, but in this case, the words are those visual tokens we were talking about.
Ah, okay. So
Yeah.
it's like the AI is watching a movie and trying to guess what's going to happen next, frame by frame.
Exactly. And to do that, they use a special kind of neural network called a transformer.
Transformers. Those are those things from, like, the movies.
Well, sort of. In the AI world, transformers are known for their ability to handle these long-range dependencies in data, which is super important for understanding videos.
Okay, so the AI is learning to connect the dots, to understand how one action leads to another. But I'm curious, how did these two different training approaches compare? Like, which one was better?
Well, it wasn't really a simple head-to-head competition. Both diffusion models and autoregressive models have their own strengths and weaknesses. The researchers actually used them to train separate sets of WFMs, almost like creating two specialized teams of AI agents.
Interesting. So they're exploring both approaches, seeing which one works best in different situations. But how did they evaluate those different WFMs? Like, how do you measure how well an AI understands the physical world?
Well, they designed some pretty clever tests. One of the big ones focused on 3D consistency. Imagine like a scene, maybe a room or something, and the AI has to generate video of it as the camera moves around.
So it's not just about making it look pretty. The AI has to actually understand the 3D space, right?
Exactly. If the AI doesn't get that, objects might warp or jump around in weird ways as the viewpoint changes.
Yeah, that wouldn't be very realistic. Kind of like a movie with really bad special effects.
Exactly. So how did the WFMs do on this test? Well, both the diffusion and the autoregressive WFMs passed with flying colors. They were way better at maintaining that 3D consistency than the baseline model.
Okay, so both teams did well on that one, but that was just one test, right?
Yeah.
What other challenges did they throw at these AI agents?
Right. Another key test was something they called physics alignment. It was kind of like a physics exam for AI.
A physics exam. Okay, now I'm really intrigued. Tell me more.
So they would show the WFM a few frames of a video, like say a ball rolling towards a ramp, and then they'd ask the AI to predict what would happen next.
Ah, so the AI couldn't just cheat by looking at the rest of the video. It had to actually figure it out based on its understanding of physics.
Exactly. And they used all sorts of metrics to evaluate those predictions, like comparing individual pixels, analyzing how well the AI tracked the objects, and all that.
So how did they score on this physics exam? Were there any, like, star students?
Well, both types of WFM showed real promise. But the diffusion-based models, they consistently outperformed the autoregressive models on this particular test. It seems like they had a slightly better grasp of those subtle physics interactions.
Interesting. So it's like diffusion models are the physics whizzes of the AI world, while autoregressive models still need a bit more practice.
Well, I wouldn't say it's that simple. It's more like each model type has its strengths and weaknesses.
Yeah.
And the researchers emphasize that both are still under development. They're constantly learning and improving.
It's exciting to think about where this technology could go in the next few years. Like, imagine hyper-realistic video games, super accurate training simulators for pilots and surgeons, maybe even tools that could help us predict and deal with climate change. The possibilities are endless.
Exactly. But along with all the excitement, we also need to be mindful of the potential challenges. As this technology gets more powerful, the stakes get higher.
Absolutely. This research is groundbreaking, but it also raises some big questions about responsible development, ethical considerations, even the potential for misuse. Like, what happens if this technology falls into the wrong hands?
It's like any powerful tool, right? It can be used for good or for bad. And that's why it's so important to have these open and honest conversations about the ethical implications, and not just among scientists and engineers, but also with policymakers, ethicists, and the public.
Yeah, we need to make sure that as this technology develops, it benefits everyone, not just a select few.
Couldn't agree more. The future of AI is being shaped right now, and it's up to all of us to guide it in the right direction.
Well said. And for those of you listening, if you're interested in learning more about this research, we'll be sure to link to the full paper in the episode notes. It's a fascinating read, packed with tons of technical details and thought-provoking insights.
Yeah, and it's a great reminder that the world of AI is constantly evolving. What seems like science fiction today could be reality tomorrow.
That's for sure. Well, that's all the time we have for today's deep dive into the Cosmos World Foundation model platform. Thanks for joining us. We hope you found it as mind-blowing as we did. And as always, keep exploring, keep asking questions, and keep pushing the boundaries of what's possible.